Okay, this is podcast 6.1 for chemistry. We're going to talk about the mole and how you can calculate molar mass. So when we're talking about measuring matter, we want to think about counting units to start with. Counting units are things like dozen, pair, ream. They're words that you say that mean a certain amount. So for example, a dozen always means 12. A pair is 2. A ream of paper has 500 sheets of paper in it. A trio is 3. A quartet is 4. So counting units, these are words that have a numerical meaning to them. When we're talking about chemistry, the most common counting unit we use is the mole. So chemists use the mole to count the number of atoms or molecules. And here is how we abbreviate it. All you do is you just drop the E. This is the SI base unit used to measure the amount of a substance. So just like length's SI unit was meters, mass was grams, the amount of a substance is going to be moles. And 1 mole of anything has 6.02 times 10 to the 23rd representative particles in it. So we can talk about having a mole of eggs, we can have a mole of pennies, we can have a mole of anything, we can have a mole of people, we can have a mole of stars. Anytime you say mole, all you mean is that we have 6.02 times 10 to the 23rd of them. Now that's also referred to as Avogadro's number, so you'll see it called the mole or Avogadro's number. They're both the same thing. And then if we were to write it out, not in scientific notation, this is how long it would be. So we're talking, this is a pretty big number that we're working with here. I have some analogies so you can get an idea of how big a mole is. So the first one is, if I had a mole of pennies, I could give each person on Earth $926 billion and still have money left over. If I had a mole of marbles, I could cover the Earth in marbles to a depth of 50 miles. If I had a mole of seconds, it represents a span of time 4 million times as long as the Earth has already existed. So that would be 2 trillion years. If I had a mole of marshmallows, I could cover the U.S. to a depth of 6,500 miles. If I had a mole of water droplets, it would take them 134,000 years to flow over Niagara Falls. And Niagara Falls, that's how many gallons per minute of water flow over it. So you're getting the idea here that a mole, when we talk about moles of things, these are really large amounts. But if you look in this picture, what we have are moles of atoms. So because atoms are so tiny, we need a lot of them in order to be able to work with them. So what you're seeing here is this is a mole of iron, a mole of copper, a mole of tin, and a mole of iodine. And these are 50 milliliter beakers, so they're the really tiny ones that we work with, the smallest that we have. And you can see that some of them are just partially filled. If I have a mole of iron atoms, it weighs 55.85 grams. If I have a mole of copper atoms, it's 63.55 grams. And you might be wondering where we get this number. Well, if you look on your periodic table and you find iron on your periodic table is element number 26, you're going to see 55.845, which they just rounded here. But that number that you're seeing on the periodic table is the mass of 1 mole of that element. So if I had, let's go to carbon. If I had 1 mole of carbon, it would have a mass of approximately 12 grams. So the periodic table, that mass, says if I had 6.02 times 10 to the 23rd of that element's atoms, that's what mass they would have if we were to put them on the scale. So we want to take a quick look at these samples and compare them. So how do these samples differ? Well, we can look and see they differ in color, they're differing in shape, and they're also differing in volume and mass if we remember back to what their masses were. How are they similar? They're similar in the way that they all contain 6.02 times 10 to the 23rd atoms of that element. So each of these have the same number of atoms in each sample. How many particles are represented in each sample? And we just said that. It's 6.02 times 10 to the 23rd. And then why are the sample sizes different if they are all 1 mole? Well, we know that if we looked at copper on the periodic table, copper is element 29. If I asked you for copper, how many protons, neutrons, and electrons does an atom of copper have? Well, copper would have 29 protons and 29 electrons because that's its atomic number. And then to figure out how many neutrons each one would roughly have, we would take 64 because we'd want to round that mass to a whole number, and we take away 29. And we get 35. So copper has 29 protons, 29 electrons, and 35 neutrons in each atom. If I went and looked at iron, because iron is close by, element 26, it would only have 26 protons, 26 electrons, and then if we did the subtraction for iron, it would be 56 minus 26, so we would get 30 neutrons. And if we went back and looked, we know that iron was 55.85 for the sample, and copper was 63.55. So each individual copper atom is bigger, it's made up of more stuff than the iron. So your sample sizes are different because the size of the atoms are different. Well, how small is an atom then? And then it says, imagine the nucleus to be the size of a golf ball. So we have our golf ball for our nucleus. Then on this scale, the first electron shell, so our first shell that holds electrons, would be about a half a mile from the golf ball. So this would be 0.5 miles away. The second shell would be about 2.5 miles from the golf ball. So if we needed to go out to the second shell of electrons, we'd have to go 2.5 miles away. And then you can just keep going and going. So even making the nucleus the size of something as small as a golf ball, we still would have an atom that is relatively big. We're talking miles here for the electron shells. So atoms are very, very, very tiny, which is why we need such a big number when we're dealing with them. And because they're so tiny, atoms, molecules, and formula units, we usually count them by using their mass because we are not going to sit there and count atoms one by one. That would be ridiculous. So we do it by their mass. If we can figure out the mass of our sample, we can go backwards to determine how many atoms or molecules or formula units we must have. And it's important to note here, atoms are if you have a pure element. So if I have just copper atoms, that's what we would say. If I have covalent compounds, though, we say they are molecules. So for example, we have water molecules, or we have carbon dioxide molecules. If I have an ionic compound, we have formula units. So sodium chloride, that would be a formula unit. Each of these is a formula unit. Sodium bicarbonate, each of those would be formula units. So these titles are all particles, but they mean different things and we use them depending on whether it's an element, whether it's covalent or ionic compounds. It's much easier to use their mass to count them. So if I know I have 5 grams of carbon dioxide, I can work backwards to figure out how many molecules of carbon dioxide that must be. If I know 1 mole of copper atoms has a mass of 63.5 grams, how could I count out 5 moles of copper? Well, I know I need 5 moles of copper, and each mole of copper is 63.5 grams. So if I just took 5 times 63.5 grams, and when I multiply that, I get 317.5 grams. So this count out really means what I would do is I would put 317.5 grams of copper onto the scale, and I would know that I would have 5 moles of copper on the scale. So we're going to use their masses to count out the number of atoms and to count out the moles. And we'll do a lab with that in class. So how do I know the mass of 1 mole of something? We've already kind of covered this. We use what's called the molar mass. That's your periodic table mass. We write the chemical formula of the compound. You're going to add up the atomic masses of each element in the compound, and the units that we put on it are always grams per mole. So I need you to grab your periodic table really quick, and we're going to do 4 practice problems together. So the first practice problem says calculate the molar mass of hydrogen gas. Well, hydrogen gas we know is a diatomic, and its formula is H2. So when you're trying to calculate the molar mass, we need to add up the mass of 2 hydrogen atoms because that's what's here. So I would put a 2 because I have 2 hydrogens, and then I'm going to go to the periodic table. The periodic table says 1.00794. Well, I don't want to use that whole decimal. Usually you only need to go to the hundredths place. So if this is your decimal, you only need to carry 2 decimal places. You are allowed to round to a whole. Round to a whole if you are within 0.0, no, if you're within a tenth of, we'll say a tenth of a gram. So if you had 18.95, that is within a tenth of a gram to a whole number, I could just say that's 19. Or if I had 1.00794, that is definitely within 0.1 of a whole number, so I'm just going to say that's 1, just like we did here. These take a little practice. If in doubt, don't round to the whole. Keep 2 decimal places and go with that. If you round too much, or when it's not the correct time to round, you'll end up with the wrong number. So hydrogen would be 2 hydrogens with each of them having a mass of 1. So the molar mass would be 2, and I would use grams per mole as my unit. There's 2 grams in 1 mole of hydrogen gas. Water is H2O. So I'm going to start the same way. I have 2 hydrogens, and I know each hydrogen has a mass of 1. Plus I have 1 oxygen. So I go to the periodic table and I look for oxygen. It's 15.9994. Again, that's close enough to a whole number, I can just say 16. So 2 plus 16 would be 18. There's 18 grams in 1 mole of water. And then our last ones here, aluminum oxide. Aluminum is a +3, oxygen is a -2. So the formula for this is going to be Al2O3. And then to figure out the molar mass, I have 2 aluminums, and looking on the periodic table for aluminum, it's 26.98 and then a bunch of other numbers. That is within 0.1 of a whole, so I'm just going to round it to 27. Plus 3, and we've already done oxygen, is 16. So to figure out that molar mass, I would take 2 times 27 plus 3 times 16. And when I do that, I get 102. Again, grams per 1 mole. And because it's 1, we don't write it, it's just assumed. The iron 3 chloride, iron is a +3 because of the Roman numeral, chlorine is a -1. So this is FeCl3. I look on the periodic table for iron and it's 55.845. A lot of times you just see that rounded to 55.85. And that is not within 0.1 of a whole number, so I've got to keep both those decimal places for iron. Plus 3 chlorines, and if I look at the chlorine, it's 35.453. If I round that to the hundredths place, it would be 35.45. Again, that one is not within a tenth of a whole number, so I've got to keep those 2 decimal places. And when I put that into the calculator, I get 162.2 grams per mole. So you need to be pretty familiar with this and be able to do it quickly and accurately in order to keep moving on with what we're doing here. And that is the end of podcast 6.1. So we'll do a lab in class on how you can count by weighing, and we'll also do some practice with calculating molar masses.